Okay, we now consider how we can use the protecting group chemistry introduced in the last lesson to achieve the practical synthesis of a dipeptide. So assuming that your amino acids are not already purchased protected, which you frequently can do actually, you would need to protect them. So if we're trying to synthesize phenylalanine on the left and valine on the right, what we have to do is Bach protect the phenylalanine and then benzyl protect the valine. And the reagents for those are Bach anhydride and benzyl alcohol under acidic conditions. Okay, so then you take the two protected amino acids, you mix them together in the presence of DCC. That's going to do the coupling, and now you have your protected dipeptide. And then the third step is to remove the protecting groups. Okay, so we use TFA to remove the Bach group, and then in this particular case, we remove, because there's no sensitive functionality in this particular dipeptide, we can remove the benzyl ester simply by hydrolysis under basic conditions, and that's now going to give us the dipeptide that we want. Okay, so if just the Bach group is protected, okay, so these two protecting groups will come off under different sets of conditions. Just the Bach group is removed, this process can be repeated as often as desired to produce a polypeptide instead of a dipeptide. And all, as I've already mentioned, all of the Bach-protected natural amino acids, at least, are commercially available, so that's going to save you some work of putting the Bach-protected groups on. So the real advance in this area is what we call solid phase peptide synthesis, and that is really how peptides are made today. So what I went over on the last slide is solution phase peptide synthesis, and the problem with that is that, first of all, that process would be very labor intensive if you're trying to make a long peptide, because with everything in solution, each peptide must be purified away from excess reagents and byproducts. And as you know, purification techniques include things like distillation, crystallization, and chromatography. Secondly, from a less practical perspective in terms of labor, but a more practical perspective in terms of materials, the overall yield of the process decreases dramatically as the peptide length increases. And the reason for that is that the overall yield of a two-step process is equal to the product of the yields of each step. Okay, so if you do a two-step synthesis and get an 80% yield out of each step, the overall yield for the two-step process would be 64%, 0.8 times 0.8. So extending this further, if you go up to a 10 amino acid peptide, and you get 80% yield from every reaction, and you should know from doing some lab work that an 80% yield is a pretty good yield for organic reactions. So if you get an 80% yield for each reaction, you're now down to a 14% overall yield, which, is just not that great. So the solution to this whole process was presented by a chemist named Bruce Merrifield, who worked at Rockefeller University in New York City back in 1963. So he worked on this process for 4 years and published the important paper on it in 1963 that still remains one of the most cited papers in all of chemistry. And he won the 1984 Nobel Prize in Chemistry for developing this method. So Merrifield's basic idea is that since the protecting group for the C-terminus does not need to be removed as you grow the peptide chain, what we do with it is we attach the C-terminus to a solid support. The solid support is a polymeric material. It's also sometimes called a bead. It's also sometimes called a resin. So that the key is that it has to be something that is insoluble in solution. So as the peptide chain is growing, the peptide that's being formed is also insoluble. So you add each additional amino acid that you want to the free N-terminus of the growing peptide chain. And then finally, as your final deprotection step, instead of removing the benzyl ester, you cleave the peptide that you want off of the solid support. Okay, so that's the basic idea. Now let's look at some of the details. Look at some structures here. So the Merrifield resin is a bead, literally, of polystyrene, so it's styrofoam. Okay, you can't do any better than styrofoam beads. Except the styrofoam is functionalized with benzylic chlorides at the para position of the benzene ring. And what those benzylic chlorides are useful for is that you can attach the first amino acid, that's going to be the C-terminal amino acid in your final peptide, to the resin through an SN2 reaction. Okay, so we're going to have the amine group Bach protected, and then we're going to have the carboxylic acid deprotonated to make a nucleophilic oxygen, and that will react with the benzylic chloride. Remember, benzylic groups are very reactive in both SN2 and SN1 mechanisms. We're doing this under SN2 conditions, and that puts the first amino acid group on as an ester bound to the resin. Okay, so then to be able to go further with this, the second step in the process would be to remove the Bach protecting group using TFA. And then finally, you will add the next Bach protected amino acid along with DCC to give the tethered dipeptide. And then you just continue to repeat this process as many times as you want. So in this particular example, we're ending up making a pentapeptide. So we would start with phenylalanine, then alanine bound to the polymer. You cleave off the protecting group. You add the next amino acid, which would be Bach protected leucine along with DCC. Now you've got the Bach protected tripeptide, cleave off the Bach group, add the fourth amino acid, glycine, along with DCC. You have the Bach protected tetrapeptide, cleave off the Bach group, and add the Bach protected fifth amino acid, isoleucine, again along with DCC. And now that gives you your pentapeptide, still with Bach protection and still bound to the polymer. So if you use TFA to cleave off the Bach group, and then in this case you can actually use HF to cleave the ester, cleave the peptide off of the resin, that gives you the pentapeptide that you want. Okay, so this idea is pretty brilliant. So, in 1969, Merrifield continued to develop this, and he reported the synthesis of a 128 amino acid long protein using this method, the protein ribonuclease, and the overall yield for it was 17%. And given that you have a couple of reactions for every coupling step, what that means, if you did the math, is that the yield for each individual reaction was actually greater than 99%. So these are really, really, really efficient reactions. And peptides are still made this way using automated peptide synthesizers. So as I said, there are biopolymer core facilities in medical school research labs. And if you need a peptide, you just give them the amino acid sequence you want, you send it downstairs, and they'll deliver you the peptide made by Merrifield's technology. Now, we don't synthesize proteins this way. We synthesize proteins in bacteria by expressing a gene when you want a complete protein. But if you just want short peptides, there's still nothing that beats good old chemical synthesis. Okay, so now that ends our mini topic on peptides. So then in the next video, we will start talking a little bit more about proteins, which is what happens when you have long chains in peptides.